Okay, so I'm going to record the video for the first lecture for slides C161 and 261. This is a class for machine learning geared towards upper class undergraduate students and also the first year graduate students. So at the same time, I'm also teaching a class stats for 13 for applied master students. So the contents for the two classes are basically the same. So I will synchronize the lectures for these two classes and they share the same video recordings. So first, let me introduce myself. My name is Yingnian Wu, and I'm a professor from Department of Statistics of UCLA. And this is my email address. So if you have any questions or concerns or comments, please feel free to email me and I will try to reply to your email as soon as possible. So currently I set my office hour for stats C161 and 261 at Tuesday and Thursday from 2:30 to 3:20 p.m. Just an hour before the class. And if this time is not good for you, we can always set up a time that is more convenient to you. And also, if you get onto the canvas and click the syllabus, you are going to see that I'm also offering a actual office hour over Zoom on Saturday, 4 p.m. So you can find the Zoom link there. And for stats for 13, the office hour will be on Wednesday from 4 to 5 p.m. Before the TA's discussion session. And again, if this time is not convenient, we can always reschedule. And also, you are always welcome to join our Zoom meeting on Saturday, 4 p.m. Again, you can find the link on syllabus. So for 413, we also have a discussion session, and I have already shared the Zoom link also for C161 and 261, so that people from that class can also join the discussion session offered by our TA, Yaxuan Zhu. So he's expert in computer programming, and the discussion session, the TA session, will mostly focus on coding. And if you don't have any background in, say, Python, it's okay, because Yaxuan will teach you how to code in Python. And I have asked him to give his TA discussion through the Zoom, because for computer coding, it is more convenient to use a Zoom so that he can share the link, and also he can record the videos. So I'm going to post his TA discussion videos and also materials, for example, some files to both classes, so that you can also review them after the TA discussion sessions. So in general, you can find all the teaching materials on Canvas. And in particular, if you click the modules, you will see some LaTeX notes. And I'm also going to upload some updated notes. And also there's a book on Python coding. So I will continue to upload the teaching materials, including this video, to Canvas modules. I think Yaxuan also posted some of his materials under the files. So if you click files, you can also see some of the content. So I think both modules and the files contains the teaching materials. And I probably will transfer most of the things on the modules, so that those things are easy to locate. So let me go over the topics we are going to cover for this class. And we start from linear regression and logistic regression. So logistic regression is also sometimes called classification. And these two types of models are the basis of the building blocks for machine learning. So later you will see that most of the machine learning methods are based on these two types of models. And also, when we study linear regression and logistic regression, I'm going to go over some basic linear algebra and multivariate calculus. After that, we shall study regularization to avoid overfitting, including L2 regularization, which leads to ridge regression, and also L1 regularization, which gives you the so-called lasso regression. And now we shall move on to study regression and the classification trees and random forests that combine the trees, and the boosting method, which also select or add the trees sequentially. So that includes the ADA boost, which is the origin for modern boosting methods. And more importantly, from a practical point of view, the XG boost, the extreme gradient boosting, which has the best performance in many machine learning tasks. And then we shall study kernel methods, which actually is a generalization for L2 regression. And we shall focus on support vector machine, which can be considered as a L2 regularized logistic regression, or at least they are related to each other. And support vector machine is a very important classification method, very commonly used before the revolution by deep learning, especially before 2012. And then we shall study deep learning, which more or less a rebranding of neural networks. So all the deep learning methods are based on different types of neural networks, including convolutional neural network, CNN, and recurrent neural network, RNN. One special class of recurrent neural network that is very commonly used is the so-called long short-term memory. And more recently, people develop transformer based on the style of attention mechanism. And nowadays, deep learning is really transforming artificial intelligence and also transforming our life. So it is very popular, and especially for the tasks where we have a lot of training data. And also nowadays, we have much better computing power in the GPU, the graphical processing units, which enables powers parallel computing. One important perspective of deep learning is embedding, which is like we embed, for example, a word in a Euclidean space, say 100-dimensional Euclidean space, or in other words, we represent entities as vectors so that we can apply differentiable operations, for example, matrix multiplication, followed by coordinate-wise or element-wise nonlinear transformation. So this is really the language of neural network, vectors and matrices. And we shall also study the generative models, which is really a very pure form of embedding or representation. And then equipped with deep learning tools, we shall also study reinforcement learning. So where for example, a robot can learn how to act based on the reward. The reward may be either immediate reward or the delayed reward. And the reinforcement learning is to optimize the accumulated reward. And then finally, we shall study AlphaGo, which can be considered as a model-based reinforcement learning, which has both search and also some like a deep reinforcement learning elements. So for the homework, we shall have weekly or bi-weekly homework, which consists of written part and also the coding part. For the written part, mostly you only need to go over the lectures or watch the videos, and so that you can replicate some of the key results that we covered during the class, or maybe a little bit generalization or extension. And for the coding part, mostly you don't need to write the code from scratch. You only need to implement some existing code, for example, the Python code, and obtain the results. About the homework, sometimes I make the problem a little bit open-ended. So which means I don't give you very detailed format or very rigid instructions. So in that case, you just interpret the question in good faith, and then we shall also grade your work in good faith. That is, we interpret what you did in your favor, or your understanding in your favor. So that part I want to specifically mention that please do not feel like afraid of what to do, just because the instruction is like a little bit open-ended. Actually, later when you do research with your advisor, or maybe you work in a company with your supervisor, most of the instructions are also open-ended, so they don't give you step-by-step instruction. And also for this class, mainly I teach it as a graduate course, which means grading is not that important. So my purpose is really to teach you something very important and very useful for your future career, so that in the future you may discover something on your own in your research, or maybe you do some interesting things in applications that are related to your future work. So that's my purpose. So therefore, you can also treat this as a graduate class, which means the focus is more on learning something useful instead of just getting the grade. Especially because this is a very interesting class, I think, a very interesting topic, and I shall also present things in the most coherent and streamlined manner, so that everything are tightly connected to each other within a unified framework. So in any case, I hope that this class will be a valuable learning experience for you at UCLA. And also for the second half for the class, we probably will use Google Colab for some deep learning code, because we need the GPU, the graphic processing unit, in order to do parallel computation. So I think nowadays they charge a small amount of money for this Google Colab if you want some decent computing. Otherwise, they will assign you to some very trashy GPU, which will take you a long time to finish running the code. So if you need any financial help for paying the Google Colab, so please just let me know. And as to the final exam, it will be mostly like a final homework or final project. So it will be take home. So you finish within 1 week I think in the finals week. Okay, so as I mentioned, my goal is really to teach you those almost all the important and modern machine learning methods, so that you may apply it to your research or your work in the future. Okay, so now let me start the real business. So we start from linear regression. And for linear regression, maybe we want to start from the simplest regression. It is even simpler than the so-called simple regression, in the sense that we have n observations, but for each observation, we only have a single input variable and a single output variable. And usually we write input as xi and we write output as yi. For example, xi may be father's height and yi may be son's height. And from this training data, we want to learn how to predict son's height based on father's height. So the word regression actually has the original meaning of regression towards the mean. So that is the son's height on average will be less outstanding than the father's height. So it go closer to the population average. So that's the original meaning for regression towards the mean. Because when you learn this model, there's also some error part, which or random fluctuation, which balance this effect of regression toward the mean, so that the population over generations can stay stable. So that's the original meaning for regression toward the mean. But later, people generalize this meaning of regression, so that regression now is understood as just finding the relationship between the input variable or input variables and the output variable or output variables. So that is both input and output may consist multiple variables in the general situation. And in terms of machine learning, so often we call this as our training data, so that each xi and yi is called a training example. So the idea for learning is that from this training data, we want to learn a model, so that this model can be applied to the testing data, where suppose I only tell you father's height, whether you can predict the son's height. So that's the basic idea for learning. And then the hope is that what we learned from the training data can be generalized to the testing data, or generalized to the whole population or underlying distribution that generate the training data. And a little bit notation. So we use xi to denote the input. Later, we shall generalize xi to a vector, and then yi is the output. So we can look at the column vector x, which consists of x1 to xn. So this is n-dimensional column vector. And the y will be y1 to yn. So this is n-dimensional column vector as well. And so this is a very useful notation for linear regression, but probably not that particularly useful for logistic regression. And our model is like this. So for each example, we assume that yi is xi times beta plus ei. So ei is error or random fluctuation. So from this example, father's height and the son's height, suppose that we measure the father's height and the son's height based on how many deviations it is above or below the population average. So this is like you standardize it, right? So you subtract the population average and divide by the population deviation, standard deviation. You get this standard value, and then we can assume that yi equal to xi beta plus ei. So the original meaning of regression, as I mentioned, for this model in this form, means that the beta is less than 1. If we measure xi and yi based on how many standard deviations they are above or below the population average. Okay, so that's the original meaning. Beta is less than 1. So that is the son's height tends to be less outstanding or more mediocre than father's height. For example, if father's height is 6'6", for example, Michael Jordan, right? But his son's height will be shorter, so less outstanding. Or if you look at other biological measures, for example, Einstein, his son is still a professor, but certainly less outstanding than Einstein. And nowadays, it's more outstanding than Einstein. So that's a regression towards the mean. So it's getting closer to the mean. That's indicated by the fact that this beta is less than 1. Okay, and but why then? But is there a danger, for example, that the population become more and more mediocre? No, the reason is that we still have this EI. EI is like a random fluctuation. That is for the same father, right? And if you look at the, if there's many, the father has multiple sons, for example, and if you look at the variation, so this EI tell us the variation. So that is this linear regression model only capture part of the relationship between X and YI, or at least part of the variations in YI. And then the other part is random fluctuation or biological fluctuation. For example, within the same family, if you look at the son's heights, they can be different. Or if you look at the whole population, if you look at all the sons whose father's height is say 6 feet, and then you look at their son's heights, then there's a fluctuation. So we assume that the EI is account for this random fluctuation, and the EI is assumed to follow a normal distribution with mean 0 and certain variance. And the reason that the population does not always converge to the mean, so that everybody has the same height, is that we have this random fluctuation. So this random fluctuation counterbalance this regression towards the mean. For example, Jordan's father, right, is maybe closer to the mean, but how come Jordan is so tall? So that's caused by this EI, the random fluctuation. Sometimes people call them a freak of nature, right? So that is in this population. So there are two forces that are taking effect. One is regression towards the mean, and the other is this random fluctuation, so that the population remain stable. So let me mention again that we measure Xi and Yi as a standardized version, that is how many deviations it is above or below the population average, and then you have the regression. The regression towards the mean means that the beta is less than 1. And in that setting, if we measure Xi and Yi by their standardized version, so you subtract the height by the population average and divide this by the population standard deviation, then beta is less than 1. And in fact, beta measures the correlation. Okay. So that's the original meaning of regression, which actually closely related to correlation. And but later, people just generalize this notion of regression. So as long as yi is a function of xi, and you try to learn this function from the training data, subject to some random fluctuation, then this model is called regression model. Okay, so the regression has lost its original meaning of regression toward the mean. And the current meaning of regression just means that any relationship, either linear or nonlinear, between y and x is considered as a regression. And the logistic regression means that yi can be even binary, positive or negative, instead of being continuous. So when this yi is continuous, we can assume a linear relationship. But if yi is a binary, as we will see in the next lecture about logistic regression, then we need an actual nonlinear transformation or actual so-called link function, as we will see later. But in any case, let's still start from this linear model. And why we call this as the simplest regression model, because we don't even include the intercept, right? Otherwise, you have to add another column of ones, and then you have this beta 0 plus xi beta 1, right, as your model. So for simple regression, we assume that we have one input variable and one output variable, but we also have intercept term. However, for this simplest regression, we don't even have intercept term. So whenever I teach regression, I always start from the simplest regression, because actually, when we later study other more complex models, we can also start from simplest regression, and we can learn a lot from it, so that we can generalize this. For example, later we shall generalize xi from a single scalar to a vector. and then we can still get we can still learn how to fit the model, how to get our estimate of this beta, how to learn from such data. Okay, so it is always a good practice to start from the simplest example, so that you know exactly what's going on. And for this simplest regression model, suppose we want to learn beta. So one important lesson for machine learning is that you always start from a objective function, or sometimes people call this as a loss function. And this is a modern paradigm of machine learning, but actually this paradigm was started by Gauss many years ago. So Gauss invented a least square method to fit the linear regression model, not just the simplest linear regression, also the multiple linear regression, which is maybe particularly relevant for the loss function. And the loss function for the least square method, as invented by Gauss, is like this. So L of beta, so we use L for the loss function, and L of beta, so this is the function of beta, a function of beta, okay? And this function is the loss function, and it is defined based on the training examples, training data. So we have summation I from 1 to n, yi minus xi beta squared. So the idea is that we want to find our beta that give us the best explanation for the data, so that under this optimal beta, this xi beta give us the best prediction of yi, so that the difference is minimized. So this is a notion for loss function. You want to find the beta with a minimum loss. And we call this as a least square loss, because the loss is in the form of the summation of all the squares of the discrepancies. Sometimes we call this yi minus xi beta as error. Sometimes we also call this as residue. So that is after we fit the linear regression model, then how much there's still left that unexplained for this yi. And for this type of function, it is quadratic. The least square function is quadratic in beta, so it's a quadratic function in beta. And for this function, we know that there's a unique minimum, and this will be our estimate of beta, so beta hat. Usually we put a hat on top of a parameter. We usually use a Latin letter for the unknown parameters in the model, and we put a hat on top of it, meaning that this is estimate computed from the training data, because the loss function is defined by the training data. Okay, so that's the basic idea for least squares. And later we shall also generalize this least square objective function to multivariate situation where both xi and beta are p-dimensional vectors. So the reason that Gauss developed this least square method was that when he was young, the astronomers found a comet, and they were very exciting. But after some time, they lost track of this comet. They don't know where the comet went because of the glare of the sun. So they couldn't locate it. So they were at a puzzle where to find it. And then based on the existing data, which only consists of a small number of observations, and then Gauss developed the formula for the trajectory based on Newtonian mechanics. So there's there's a sun, right, and there's a Earth or some other planets, and the motion for the comets is mainly under the influence of the sun, but also the influence of other planets. So the underlying mathematics is quite involved, but certainly that posed no difficulty to Gauss. And he developed this equation, which is actually a linear equation, so that you can predict the position of this comet based on some underlying variables. But he needs to estimate the coefficients of those variables in this regression model, and he used the least square method to estimate those coefficients. And then he was able to predict the position of this comet at a certain time. And then he asked the astronomers to aim their telescope to that position. And not surprised, those astronomers found it. So Gauss became a celebrity at a very young age. And but somehow Gauss feel that this least square method is a bit trivial, so he didn't really care to publish it. And then about the same time, another scientist, Legendre, he also developed the least square method, and the two later had a dispute about the priority as who was the first one to to develop this least square method. But anyhow, that's not related to our study. So now let's continue. So suppose we want to find this beta hat by minimizing this loss function. And then we only need to find a stationary point, right? We want the first derivative to be 0. The first derivative is the slope. And we want the slope to be 0 at the beta height. And we also, let me close the window. There seems to be some noise outside. And also we want to compute the second derivative. And if this is a minimum, then supposedly the slope change from negative to 0 to positive, so that the second derivative, which is the change of the slope, should be positive. Okay. So now let's compute the first derivative. So the first derivative of beta is we have this summation, and then we use the chain rule, right? We first take derivative of the squared. It will be 2 times. I think we may have 1/2 here. We add 1/2 here, and then the 2 get cancelled, and then we have yi minus xi beta. Okay, and then we need to take derivative of this one. So the derivative of this term with respect to beta, that will be negative xi. So I just put a negative here and xi here. Okay, so we can see that this is actually, this yi minus xi beta is the residual. We may call this as ei, right? So this is summation of ei times xi. Later, we will see that this is an inner product between the two column vectors. But for now, let's try to solve this equation. So that will be summation yi times xi, right? And we move this, the second term to the right-hand side. So we have summation xi beta times xi squared times beta. Okay, and then we solve beta hat, which is a summation xi yi divided by summation xi squared. Okay, so this is a square estimate. And then we can also compute the second derivative, which is the summation of xi squared, so that indeed this second derivative is positive. And this is true for any beta, and certainly it is also true at beta hat. So the fact that the second derivative is a positive means that this function is a convex function, and it has a global minimum at the beta hat. Okay, so therefore we have learned our first like machine learning problem. So we solve our first machine learning problem, and this is our training data, and this is our model, and this is our loss function, and this is our estimate. Okay, so now you see that the steps that we have, right? We collect our training data, and then we try to learn a model, either linear or nonlinear. And then we come up with a loss function, the least square loss function. And then we estimate our beta, or we learn this beta by minimizing this loss function to get our beta hat. So after we learn beta hat, we can apply this to the future testing examples. So this is a step for machine learning, and for other machine learning problems that we shall study later on, we always follow the same steps. And in particular, this machine learning problem is called supervised learning. So that is for each input xi, we also have a output yi as a supervision. So we have a supervision for each training example. And so that we only need to learn how to predict yi based on xi. So this is supervised learning. And later we shall study unsupervised learning and reinforcement learning. So for unsupervised learning, we don't have yi. We don't have a label or a annotation of yi. We only have xi, and we want to figure out the underlying structure of xi. And for reinforcement learning, for example, this xi may be the state, and the yi is action, but we don't observe this action in the learning process. So therefore, what we want is to learn how to predict the action in order to maximize the overall cumulative reward. So the learning signal or the feedback come from the reward instead of a direct yi. Unless we are doing the imitation learning, we learn from a teacher, then we have supervised learning. Okay, so in any case, so here this is a simplest example of supervised learning. Okay, so now let us view this simplest regression problem from a different perspective. So from the column vector perspective. So we use this x as a column vector, n-dimensional column vector for x1 to xn, and the capital Y as an n-dimensional column vector from y1 to yn. And from a vector perspective, so we have x and y, and then we also have e. So E is the n-dimensional column vector that collects E1 to En, where this EI is yi minus xi beta. Okay, so therefore now you see you can write this whole thing, this vector, as vector y minus x times beta. So here we need to be a little bit careful that x is a n by 1 vector and beta is 1 by 1 scalar. So usually you put a scalar on the right hand side and then you have x beta, so that this give you n by 1, right? N by 1 vector based on matrix vector multiplication rule. Okay, so we write this as y minus x beta. And now we can actually view the data in two perspectives. One is a scatter plot. So in this scatter plot, each point is a xi, yi. So we have cloud of points. And then our regression line is y equal to x beta. So supposedly this goes through the origin. So this regression line is y equal to x beta. These are lowercase y and lowercase x. So just representing this line. And then for each observation, xi, yi. So if we look at the difference between yi, observed yi, and the predicted yi, so this difference will be our ei. And for this example, the difference between observed yi and predicted yi, that's also our ei. Okay, and our e vector is n-dimensional vector that collects all those ei. So this is a scatter plot. It is very intuitive, and it is in the two-dimensional space. So each point is a training example xi, yi, and we want to find the regression line so that it gives us the best fit for the whole data cloud. But for linear regression, another probably even more fruitful point of view is a vector plot. So that is, we have those n-dimensional vectors, and we plot them in the n-dimensional space. So that x is a vector and y is another vector, and e is the vector that is a difference between y and x beta. So beta is a scalar. So x times beta, here I also use a beta times x. It doesn't matter, because sometimes people write a coefficient times a vector as beta times x. But if we want to be strict about the matrix multiplication, we should use x beta. Okay, so this point is x beta. So in any case, x beta is a vector that is share the same direction as x. So it may be any point here, or maybe as opposite direction as x. So any point here. So that gives us a vector. And if we look at the least square loss function is 1/2 summation ei squared. So here we put 1/2. Actually, even here we should put 1/2 here, so that when we take derivative, the two get cancelled. And usually when we have the least square term, we write this 1/2, and then this is 1/2. You see this 1/2 yi minus xi beta squared, and yi minus xi beta is ei. So therefore, this is 1/2 summation ei squared. And then this can be written as a 1/2 and L2 norm of E, or the squared norm of this E. So a square norm of a vector, it means just the square distance between the tip of this vector from the origin, right? And this can be written as a sum of squares of the individual elements. So this is 1/2 y minus x beta squared. So this is, again, a square norm. And then if you look at this loss function. So suppose we want to minimize this one. So that means we want to minimize the square length, right? This is square length of this E vector. And then clearly we should find this point, beta x, or x times beta, to be the projection of y onto this line of x. So that's a projection. So geometrically, least square method can be understood as a projection in order to minimize the error. As a result, because this is a projection, so this E vector should be perpendicular to this X vector. So the inner product of E and X should equal to 0, or in other words, E is orthogonal or perpendicular to X. And you can see that this equation is exactly the equation that we derive by taking derivative and setting the derivative to 0. So that is, if you set the derivative to 0, again, there should be a 1/2 here, and then you have this term, and this is ei, right? So you have ei times xi, sum over n, and clearly this inner product between e and x, and this equal to 0, and this is exactly what we have. So e should be perpendicular to x, which means the inner product of e and x, which is e summation ei times xi, which is summation yi minus xi beta times xi, this equal to 0. Okay, and then you get this this result. So that is our geometric understanding based on this vector plot. Also give us a geometric interpretation for the least square estimator, and also this orthogonality condition. Okay. Okay, so I think we can continue to move on to study later. We shall study the vector situation. So that is, we can generalize this xi, each of this xi as a p-dimensional vector. So that later we shall have p predictors, say, and we denote them as xi1, xi2, xij, xip, where j indicates the variables, and p, we have p predictors. So p stands for predictors, and n stands for the number of observations. So this is a commonly used notation in statistics, where n and p, they have their special meanings. And we also have yi. So y is a vector. And then now, instead of a single x vector, we have multiple x vector, and the j's column is xj. Okay, so now we have two different ways of viewing the data, and for each row, we call this as a row vector. So xi, we denote xi to be a vector of xi1 to xip, but here this is xi transpose. So we make the row vector. And correspondingly, we also have beta. Beta is beta 1 to beta p, so that now the regression model become yi equal to summation j from, sorry, this is a typo, j from 1 to p, j from 1 to p, xij times beta j, and plus ei. And then we can also write this as this xi transpose times beta, where beta is a p-dimensional vector, and this can be written as also as an inner product between xi and beta. Okay, so this is how we generalize. And then in terms of vector, this is whole vector y, and this can be written as x1, the first column times beta 1, plus until xj, j's column times beta j, until xp times beta p, plus the e vector. So you can also write this in the vector form. And then from here, you will see in the next lecture, we also get this result, that is y minus x beta times x equal to 0. Okay, so here we, for this original, for this previous example, in the simplest regression setting, right, we have this e and x, so this equal to 0, and in this regression setting, so e is y minus x beta, e equal to y minus x beta. So x is still just a single vector and times x, so this equal to 0, and then we have yx equal to x and x, right? Beta equal to 0, and the inner product of x with itself is x squared, the square norm, and then we have beta hat equal to the inner product yx and x square norm. Okay, so that's what we have, which, and this one agrees with this perfectly, right? But in this general setting, we can write this whole x as a matrix. So this is n by p matrix, and y is still a vector. And then we can write this beta hat in this general situation to be x transpose x inverse x transpose y. So this one is the generalization of this one. And also, we will see that in the multivariate situation, so this xi become a p-dimensional vector. And then we can also write this one. We can generalize this one to summation xi transpose inverse, and then summation xi yi. So I want to make clear that this is a generalization to multivariate situation. And this one is also a multivariate generalization. But this is for still the simplest regression situation, where we have univariate xi and univariate yi. But this will be for multivariate xi. Okay, so this is for multivariate, this still univariate, and this one agrees with this one, with what we have here. Okay, so therefore, to parse these equations, let me make it clear this line. So this is for univariate, and this is for vector version, but this is for multivariate. We are going to study the multivariate version in the next lecture, as I wrote here. And then this is still for univariate. That's where we got univariate here. But this part is for multivariate. So the idea is that the univariate simplest regression is a special case for multivariate, more general regression. And this is a data set we are going to study in the next lecture. I think maybe I can stop here, and let me stop the recording.